Okay, thanks, Craig. I would like to thank the opportunity to share this section. This will be a section about mapping strategies. We have 7 presenters, and the first is Pedro Menandro. He's a PhD student from the Federal University of Espírito Santo in Brazil. Okay, Pedro, please.
Okay, let me share the screen.
Okay. It's okay.
Okay.
Yes.
Well, my name is Pedro Menandro. I am a PhD candidate in my second year in the Federal University of Espírito Santo in Brazil. My supervisor is Professor Alex Bastos. Well, it's a pleasure to be here attending GeoHub. It's my second time. And thank you for all the organizing committee, especially in these challenge times. So the title of my work is Exploring Multifrequency Backscatter Response in Soft Bottom Habitat using a three-front approach. So first of all, I think it's important to contextualize this work within a huge and important and cross-disciplinary theme that is the seabed mapping. Seabed mapping has gained more and more notoriety and with many applications such as marine spatial planning, seascape ecology, and habitat mapping, and also is one of the goals of the decade of ocean science. And one of the relevant terms within the seabed mapping is the seabed classification. Seabed classification can be carried out using multiple scales with many approaches and data sets. And one of the data sets most useful and important is the backscatter, and more recently, the multispectral backscatter. So this set of topics structured this presentation, which we follow this order shown here. First, a brief introduction with a literature review of multispectral backscatter, some information about the data collected and the research methods, and results and discussion with some future directions. So over the last 2 decades, multi-beam echo sounder has positioned as the most important tool for the acoustic seabed mapping. Backscatter is considered an important predictor of the seabed classification and a surrogate for benthic habitats and other seabed properties. And in the context of the GeoHub, Harris and Baker in the last GeoHub Atlas pointed out the backscatter as one of the most useful and measured data sets in the published studies. So now the multispectral backscatter, the advantage of using such a system for seabed mapping have already been reported since 2015. Guy, Brown, and Costa et al. Investigate and present the first results of multi-beam multispectral survey. These authors observed, among other important achievements, the bare discriminatory power of bottom type as a result of multi-frequency dataset. More recently, Rania et al. Tested the potential application of using multi-frequency backscatter to predict sediment grain size. But until now, no single study has yielded sufficient evidence to address the limitations and challenges of working with multi-frequency backscatter data. In addition, there are no studies in sites with a thick mud deposit. So herein, the main objective is to describe and analyze multispectral backscatter data on a multiple methodological framework. So here we used a value-based analysis, an image-based analysis, and angular dependence, which makes it possible to integrate these results for a better understanding of the acoustic response. Okay, so here's some information about the data collected. Here is the map of the study area. The survey area has 37 square kilometers. Is located on the eastern Brazilian shelf in the state of Espírito Santo, close to the Doce River mouth. This area was already characterized by Quaresma et al. And other studies as a predominantly muddy region with a mud deposit center south from the Doce River mouth. And from 25, 30 meters, the predominance is a sandy seafloor, sandy facies. So here the Batimetry and Backscatter were acquired by Ultrasonic 2024. The operating frequency was 107, 208, 400, and 700 kilohertz. All the systems were integrated into the QPS Quincy for the acquisition, and post-processing was carried out using Chimera and FMGT. And the data were exported at the 2 meters spatial resolution. So here's the summary of the methodology. So after the processing and frequency filtering of the multi-frequency backscatter, we applied these 3 approaches. The first one is the value-based analysis, which is basically the visual interpretation of the mosaics, and also some profiles and graphs with software ArcGIS and Haar. The second one is the image-based analysis. We use here the GLCM script on Haar to extract some textural parameters. And the third one is the angular range analysis. Here's some information about the near nadir region and far nadir region. So we extract this information by the FMGT tools. And these results, combined with the bathymetry and background studies, we try to discuss towards understanding the acoustic response of multi-frequency backscattering muddy bottom. So here the first results, the digital bathymetry model with depths ranging from 10 up to 32 meters. The seafloor is predominantly flat with some steep features here and also well marked here in the slope and ruggedness. And this important feature here for this work, an oblique and elongated feature, well marked here in this bathymetric profile. So here the results for the backscatter. The first analysis is the value-based analysis. So on the left-hand side, you can see the 4 mosaics for each frequency with lower backscatter values in the shallower region. And this feature already mentioned in the bathymetry outlined the higher backscatter values. Here the frequency of 700 kilohertz. It's important to highlight that these frequencies do not work well in depths greater than 20, 25 meters. So this coverage area is different. It's smaller than the others. Here in this profile on the right-hand side, we can see a profile across all this area. In the region with lower backscatter values, we can see lower difference between the frequencies. And in this region with higher backscatter values, here the black frame is a zoom in of this profile, showing us the greater difference between the frequencies, mainly for the lower frequencies that resulting in lower backscatter values in this region. And here the violin plot shows us the lower median backscatter value for the lower frequency of 107 kilohertz. And for both 208 and 400 kilohertz, we observe a similar shape of the distribution of backscatter values, which recognizing 2 main sets of values. So the second analysis is the image-based with GLCM script. So here we can see the part of the results just for the frequency of 107 and 400 kilohertz. The general trend can be well visualized by the result of the variance, is the second one for here and here. It should be noted that the larger variations in parameters occurs as the frequency increases. And well, we are still working on this data. Maybe the next step would be check the collinearity between the variables, maybe by Pearson's correlation, and consider all or not the GLCM features for the final analysis. And the backscatter angular range analysis, the results demonstrate for most of the area a tendency toward the decreased backscatter level as the incidence angle increases. So here in this figure, in the left-hand side, the second column is the near nadir region, and the third column is the far nadir region. So we can note the backscatter level loss for all the frequencies. The exception occurs over the oblique feature here, which marks a region of higher backscatter and slight backscatter level loss for all frequencies, and also a high acoustic impedance. And in right-hand side, you can see the angular response curves. So this region A is a region with lower backscatter values. So is these four graphs. We can see a great backscatter level loss at greater incident angles, mainly for the higher frequencies here in the 400 and 700 kilohertz. While for this region B, in the higher backscatter region, the flatter shape for the angular response curve can be observed, similar to sandy sediment considering the APL model. So to summarize the results, all parameters calculated from the GLCM script indicated the bare distinction of two main sets of data as the frequency increases, which is fully consistent with the visual analysis of the mosaics, as well violin plot, and also with the angular range analysis. An important information here is from Jackson and Briggs' paper that the scattering interface is a more important factor in sandy bottoms, while the volume homogeneity of the deposit is dominant for the acoustic response in silty bottoms. Here we observe that the flatter the angular response curve, the better recognized this type of seabed will be in the textural analysis, corroborating the greater influence of scattering interface in sandy bottoms. So, although the investigation performed here did not involve accuracy metrics based on ground truth, we are satisfied with the acoustic seabed classification in soft bottom that managed to distinguish two main bottom types. So here in this figure, we can see lower backscatter values, lower variance for the GLCM parameters, and several decrease in the backscatter with increasing incident angles. On the other hand, higher backscatter values, with exception of this lower frequency, a higher variance and anomaly in homogeneity for the GLCM parameters, and a flat angular range curve that managed to distinguish these two bottom types, which would be muddy bottom and sandy bottom. So some future directions in this research would be try to measure the contribution of each approach for these results, explore the results through a composite image, RGB, try to apply this framework to other seabed types, such as rhodolite and reefs, and also try to investigate the feasibility of developing a classification model based on these results, or even implement these results in a model already existent. So some reference here, and thank you very much.
Thanks, Pedro, for the presentation. We have time to questions. You can use the chat to ask questions. Pedro. Questions? Gary, please.
Pedro, nice talk. Enjoyed that. My question is, will you ground truth this information? It seems like this is a very sophisticated approach, and now you're able probably to get down to even predicting what the grain sizes may be. But this is all dependent upon being able to ground truth this information and to run some grain size analysis to assist you in really sort of refining this methodology. So I'm wondering if you are planning on this work that you've done to collect some sediment samples that could help you in ground truthing your information. Thank you.
Thank you, Gary. So actually, there was a try to attempt to collect some drop cameras images, but due to the turbidity of the water, the images were like blurred, so not a good result. And this data set is part of a huge project that there are also other sedimentological analysis and chemical analysis. So maybe I can take advantage of another data set to try to improve this analysis with, for example, the grain size and other issues.
Thank you.
Okay.
Thank you.
Another question from the Ben Vitrolio.
Hi. I was wondering if you got any sense from the wide frequency range you used, if you see maybe transitions between what you get in the backscatter at the lower frequency ranges that would indicate where the transitions might occur in order to sort of compress that frequency range. I don't know if that makes sense.
I think I didn't get the question.
I guess did you get any sense of where transitions between backscatter response and frequency would maybe start to emerge, say between like 100 and 200 versus 200 and 300?
I'm not sure if I understand, but the frequencies are set in the equipment, and just this frequency, there are no frequencies between 107 and 208, just the set frequency. So I'm not sure if this is sufficient for you.
I'll email you. I'm not phrasing it right.
Okay. Okay.
Another question from Benjamin.
Hey, Pedro. Great talk. That was really interesting. I was wondering what constrains your choice of frequencies for the system. Like, are you able to choose basically any frequency you want? And so I also like, why go all the way up to 700, I guess? What about like 500 or 600? Maybe get a bit more depth out of those.
Okay, the frequency, it's because the limit of the equipment. So the 2024 works in a wide band. So the lower frequency is the 170 kilohertz, different from the 2026 that is 100 kilohertz. And the higher frequency for 2024 is 400 kilohertz. And we have a tool, we buy a tool to apply this 7 kilohertz, which would be the I forgot the name, the higher frequency, the higher resolution, super high resolution. I'm not sure how the name. So the choice of this frequency was based on the limit of the equipment.
Great, thanks.
Thank you.
Okay, more questions to Pedro? Yes, from Lapis. Pedro, just to be sure, as you do not have the, as you do not have the antenna 2026, means you did the same line many times with different frequencies, isn't it? I
No.
mean, you couldn't collect the different frequencies at the same time. Yes.
Actually, the pings are sequential pings. So each ping in one frequency not did the same line 3 times. So it's sequential pings with any ping in each frequency.
Okay. Thanks, Pedro. It's the first work is in Brazil with multibeam. Yeah.
Yes.
Okay. It's
Thank you,
a great work from you and your team, from Alex. Okay. Then, okay. We move to the next presentation. It's from Alex Ilich, from a PhD student from South Florida. Okay.
Thank you. Okay, should be this one.
Yes.
Okay, you see the right screen, not
Yes.
presenter view? Okay,
Yes, it's
perfect.
okay.
Okay, hi, my name is Alex Ilich. I'm a PhD student at the University of South Florida College of Marine Science, advised by Dr. Steve Murawski. I work on mapping offshore hard-bottom areas on the West Florida shelf using multiple different spatial scales of analysis. So this work was done as part of the seascape project, which works on mapping important habitats for reef fish on the West Florida shelf. We use two main technologies to do that: a multi-beam sonar to get bathymetry and backscatter data, as well as a towed underwater video camera. The system is towed behind a research vessel a couple meters above the sea floor, so that we can get imagery of the bottom to look at the habitats and also observe the fish that are utilizing those habitats. So for most of this talk, I'm going to focus on a case study in an area known as the Elbow, which is shown here. It's offshore about 145 kilometers west of Tampa, Florida. It's hypothesized to be an ancient sea level stand, and it's a hotspot for fishing in the offshore environment. The goal of this study was to map the substrate in this area using statistical approaches that relate what we're seeing in the camera as the substrate to quantitative values we get from the multi-beam, so like the bathymetry and the backscatter values. And I did that using 3 training transects, and these were transects done with our video system in the solid lines. And then that dotted line was a video transect that was reserved for accuracy assessment to look at how well we were making those predictions. So if you're interested in seeing the full details of this study, it was recently published in Geosciences for the special issue related to this conference. So if you're interested in that, I encourage you to check it out. In this study, I utilized 2 different types of statistical approaches, an unsupervised and a supervised approach. Unsupervised classification is basically just clustering, so you group similar things together, and then you bring in the video afterwards to try and back out how those clusters relate to what you're interested in. Whereas in supervised classification, we directly try and predict what we're interested in, meaning substrate, and you fit a model that does that. So the unsupervised classification method I used was k-means clustering. I reduced the number of variables going into that clustering algorithm using principal components analysis, and I interpreted the clusters using the observations from the video. For the supervised classification, I used a random forest classifier with some modifications to deal with imbalances in our different class sizes. And then also I used variable selection to reduce the number of variables going into those models. So the predictors in these statistical models are bathymetry and backscatter, as well as some secondary features you can derive from these 2 original data sets. For bathymetry, that's terrain attributes that describe the shape of the seafloor. And that includes things like your local mean, which is just a smooth version of bathymetry, the local standard deviation, which is a measure of rugosity or the roughness of the seafloor, the slope, the aspect, which is the direction of slope, and the topographic position index, which indicates whether an area is a local high or low. For backscatter, that includes first order texture metrics, such as your local mean and local standard deviation, as well as the second order texture metrics, meaning they look at the relationships between neighboring pixels. And those are all calculated using these GLCMs, or gray level co-occurrence matrices. Each of these different predictors was derived at 8 different spatial scales of analysis. using kind of your standard 3x3 cell GIS window all the way up to a 69 by 69 cell window. And since this surface was 10 meters in resolution, that's looking at things that are 30 meters in spatial scale to 690 meters in spatial scale. For the response variable in these models, we're trying to predict substrate, so whether an area was sand or whether it was rock. I'll also note that there are various morphologies of rock in our study area, from flat, low relief areas to steeper, high relief areas, but I'm mostly going to just focus on predicting sand and rock. So as I mentioned earlier, I had 3 transects used to train the model. Along those transects, we classified the substrate every 15 seconds. So you can see those classifications along the transect here. And then again, there is that validation transect, which is used for accuracy assessment afterwards to assess how well we made predictions. So for the unsupervised classification, I was able to reduce the original set of 130 different predictors down to 9 important principal components. These explain 86% of the variation. And then I ran these retained principal components through a k-means clustering procedure with 4 clusters. That results in a map of acoustic clusters that looks like this. We can then use the ground truth observations to tie these clusters to a substrate type. So we see that clusters 1, 3, and 4 mostly contain sand, whereas cluster 2 mostly contained observations of rock. So we can then get a thematic map of substrate, and we can use that validation transect to look at how well we're making predictions. Overall, we have 97% accuracy, which sounds good until you think, well, a lot of the observations are sand because we have high class imbalance. So if you just guess sand, you would have very high accuracy. So it's really important to look at some of these other accuracy metrics. Particularly a standout one is this producer's accuracy for rock is very low at just 36%. And that means that of the observations that were truly rock along that validation transect, which was 28, only 10 of the 28 were predicted correctly. Conversely, if you look at along that validation transect, all of the observations it predicted as rock were correct. So that means that the model is being very overly conservative in predicting rock and only predicting it when it's very sure. And if we look at the Kappa score, which adjusts overall accuracy for what could happen by random chance and ranges from 0 to 1, we see that we're in the threshold of moderate agreement. So the model's doing fairly well, but has some room for improvement. For the supervised classification, we retained 12 of the original 130 predictors. The rest were either unimportant or redundant. And when we look at the variable importance, this is the result. We see that the slope at 11 by 11 cells was the most important, followed by backscatter standard deviation at 27 by 27 cells. And this underscores a lot of kind of a very common finding in habitat mapping studies, which is that slope is an important predictor of various aspects of habitat, that including both bathymetric and backscatter-based features can improve your model, and also that it's important to include multiple different scales of analysis. When we look at the results of the supervised classification, this is the final map. When we conduct the accuracy assessment, we see that we're doing quite a bit better. The user's accuracy for rock has gone down a little bit, but that producer's accuracy has jumped up a lot. Before we're at about 36% and only getting 10 of them right. Now we're getting 23 of the 28 correct. And the Kappa score has jumped up to 0.75, putting us in that substantial agreement threshold. In addition to looking at the average uncertainty for our study area in kind of this traditional confusion matrix framework, we can generate an entropy map to look at how uncertainty varies over our study area. So here areas in blue represent low uncertainty and areas in red represent higher uncertainty. And that's because predictive models like this are able to output class probabilities. So you can look at how certain the model is. And that's useful for seeing how the uncertainty varies over space and where you can place future ground truthing efforts to potentially reduce that uncertainty. When we look at the two maps side by side, we see that they look very similar. And we can plot a difference map to highlight where they are similar and different. The legend here is formatted as supervised classification / unsupervised classification for the areas of disagreement. We see that there's a lot of green, and in fact, that they agreed over 98% of the time. We can also use Kappa in a similar way as before, where we are comparing predictions to observations, but instead use it to compare two maps. And we see that overall there was substantial agreement. Mainly the differences tend to occur along these edges of rocky habitats. And also we can see that the supervised classification tends to be predicting more rock, particularly in areas over here and here that are outside of where the model was trained. We can also break Kappa into two related statistics. One that looks at the class frequency, meaning how often it's predicting one class versus another. And there's near perfect agreement in that. And you can see that with the areas, they're not too different between the two different maps. And then we can also look at the spatial allocation, meaning where in the map it's placing those classes, which there was also near perfect agreement. As I mentioned, the supervised classification had a higher Kappa score than the unsupervised classification. And we found that difference to be significant using a Monte Carlo permutation test with a p-value of 0.001. So that closes out my study in the elbow, but I'd like to extend this framework to map other areas on the West Florida shelf. So here's the study area I just talked about, but we have collected multi-beam for about 2,350 square kilometers. So shown here. And then there's also existing multi-beam from previous work for these areas that are in high resolution. And that includes data collected by USGS and other faculty at the University of South Florida, such as Dr. David Nahr, Stan Locker, and Al Hine, who have done quite a bit of mapping work prior to the Seascape project. So I'm going to move out of just talking about that one area and now use 45 transects that we have from across several different study areas. I'm going to fit only a model based only on bathymetric based features, just because backscatter is not a calibrated metric, so that can be difficult to use when trying to fit a single model that goes across several different study areas, especially if those were collected using different frequency sonars and there's no overlap between some of the areas. I'm going to do it at 5 different spatial scales of analysis, from 3 by 3 cells to 17 by 17 cells, so 30 to 170 meters in scale. And then I'm going to use 10 transects for accuracy assessment in completely different areas, so down here and up here, to see how the predictions stack up when we're extrapolating well beyond where the model was trained. When we fit the model and look at the variable importance, we get these 5 important variables. Slope at 11 by 11 cells was again the most important predictor. And it's also worth noting that this topographic position index at 17 by 17 was included as an important predictor in the previous model. So this may indicate that these are relevant scales for looking at these terrain attributes on the West Florida shelf. When we run the predictions, we get this resulting map of substrate. It covers 9,100 square kilometers at 10 meter by 10 meter resolution. And when we do the accuracy assessment on these transects up here and down here, we get an 83.4% overall accuracy and a Kappa score of 0.46, which puts us in that moderate agreement threshold. So the model does okay, but there's definitely some room for improvement as I further develop this model. I was interested in digging a bit into where the model was failing. And so I found some interesting things in this area down here. So I'm just going to zoom in there. And here I put the observations that were correct in green, and then the ones where there's disagreement in black. So these are from our video where the substrate doesn't match the prediction. And if we actually go here and look at what the video looks like, we see that it is a sandy area like predicted, but that we have these sponges sticking up, which indicate that there's hard bottom beneath for these sponges to attach. So we actually consider this to be a covered rocky habitat. And this might just be difficult to predict with a bathymetric-based model only. Whereas if we were including backscatter, if the sediment layer was thin enough, we might get that strong return from the underlying rock. So to close out with some conclusions, both the unsupervised and unsupervised maps had substantial agreement with one another, but the supervised classification did have higher performance. Slope was found to be an important predictor, and including both bathymetric and backscatter information can improve model performance. Different predictors may be important at different spatial scales. And lastly, when extrapolating predictions to a wider range of areas, using just the bathymetric-based features, we found moderate agreement, but this type of model may be limited in its ability to identify lower relief or covered hard bottom areas, though I am developing models that use both bathymetry and backscatter for individual sub areas, like I did for the elbow at the beginning of the talk. Here are my references. And then I'd just like to acknowledge my lab mates and collaborators, my funders, and of course the GeoHab 2021 organizers. And if you're interested, here is some contact information and resources. I've included my email, link to the paper if you want more details, the project website, and also an R package I created to calculate those GLCM textures on GitHub, just because I had some issues with some of the existing implementations of that. With that, thank you, and I'll take questions.
Okay, thanks, Alex. Questions for Alex? Yes.
I see a question from Karen.
Karen, yes.
Have I tried incorporating any physical grain size samples along with the visual ground truth? A little bit. I haven't messed with it too much, but for some of the cruises that we did collect grain size. And I've dug into that a little bit, but not too much. There were some relationships between kind of, if I made the backscatter a little bit coarser and averaged things, there was a relationship between grain size and the backscatter, if I'm remembering correctly.
Okay, more questions? Yes. Can you read?
Yes. So for the GLCMs, did you change other parameters than the window size, such as the interpixel distance and the angle? No, I didn't change the interpixel distance. The angle that I included was I did the average across all the different directions. So like horizontally, vertically, and diagonally, and then averaged the results of those four so that it was directionally invariant.
Okay. Clary Haar, please.
Hi, I just had a question if you had considered expanding the amount of classes you had, potentially even to have like a mixed class, or trying to classify like the fraction of rock versus sand, and if that would be beneficial for like the purposes you're using this.
Yeah, that is something I think a lot about, because basically as you expand the number of classes, it always becomes harder to predict things, and it's always nice to think of things in neat categories, but a lot of times we do see like mixed classes, and generally I'll consider those to be rocky. Our camera is forward facing, so it's hard to get percent cover as opposed to if it was downward facing. And we have a lot of areas where there's covered hard bottom. So it's hard to tell then what the percent cover would be. So it's just with mixed classes, I've had trouble figuring out a consistent way to like create those thresholds.
Thank you.
Okay. A question in the chat?
Oh, yeah. I'll share that again. Hold on. Share screen. Okay, I think that should come up now. The GitHub package is GitHub, and it's at Ilich, which is my name, followed by GLCM textures. Yeah, and I just made that because I had some issues with existing implementations where either the parameterizations weren't clear in the documentation, or I was getting weird values. Like I was getting like correlations of 50, which shouldn't exist. So I ended up just making it myself.
I can't see your last slide.
Oh, you can't. Is it showing up for other people? And here, I'll try sharing.
Or put it in the chat. Put it in the chat. So if you
oh yeah, I'll just put it in the chat. I'll put it in the chat. Yeah.
Okay,
Yes.
thank you.
Copy the link in the chat, please. Okay.
Yeah.
Thanks for the great presentation. Thank you, Alex.
Yeah.
Then we are moving for the next. It's from Clary Haar, an undergraduate student from Dalhousie University.
Okay. Okay, perfect. Hi, everybody. My name is Claire Haar. I'm a recent graduate student from the University of Guelph in Ontario, Canada, where I studied environmental geomatics. And since July of 2020, I've worked as an undergraduate research assistant for Dr. Craig Brown in the Seascape Ecology and Mapping Lab at Dalhousie University. During this time, I worked on a smaller project as part of the Ocean Frontier Institute's benthic ecosystem mapping and engagement project, or the BECOME project. And the aim of my project was to apply new bulk shift backscatter harmonization approaches to multi-source data sets available for the Bay of Fundy. So today I'm just going to go over a brief overview of my project, an overview of multi-beam echo sounders, backscatter, and some calibration issues with backscatter, new backscatter calibration approaches, particularly the bulk shift, and how I harmonized the Bay of Fundy data set. And so continuous or harmonized backscatter data is needed for habitat classification applications, but this can be difficult in complex and multi-source data sets like the Bay of Fundy. For this project, we applied new bulk shift approaches that have been developed as a solution for harmonizing legacy backscatter data using areas of mutual overlap for relative statistical calibration. For those unfamiliar with backscatter, I know we've talked about it a little bit today, but essentially multi-beam systems record the intensity of echoes from or returned from the seabed, known as backscatter strength. And once the appropriate geometric and radiometric corrections have been applied, computed backscatter strengths represent the relative acoustic reflectivity of the seafloor, which is commonly used as a proxy for seabed substrate properties like hardness and roughness. And before we move on, I'd like to give a special thanks to the numerous researchers who have done amazing work collecting and working with the Bay of Fundy datasets before myself. But for use in this project specifically, cleaned bathymetric and processed backscatter grids were supplied by the Geological Survey of Canada, with bathymetric processing done by the Canadian Hydrographic Service to correct for motion artifacts and tides. An additional thanks to the University of New Brunswick, who took part in the data collection and distribution. And lastly, as part of the Hydrography to Biology project funded by the Department of Fisheries and Oceans, ground truth data was collected within the Bay of Fundy to inform the prediction of habitat maps. And so essentially in the Bay of Fundy, we have full multi-beam coverage and ground truth data that we want to use for habitat mapping, but there has been little research into methods for dealing with the multi-source nature of backscatter. So data was acquired between 1996 and 2009 from a variety of survey platforms using a variety of different multi-beam systems. These data sets vary substantially with respect to their date of acquisition, the sensor type, and the acoustic frequency, all of which impact backscatter response. So previous work evaluated different strategies for dealing with the multi-source data for the production of benthic habitat maps, but few studies have researched ways of harmonizing the data sets. So the initial intention of the project was to apply an approach similar to that presented in Lacherie et al. 2018, where each multi-beam coverage was classified separately, and then the classified outputs were combined for each data set. However, it became obvious due to the highly fragmented nature of multi-beam coverages in the Bay of Fundy that this strategy would be extremely challenging. Additionally, approaches such as this require ground validation or ground truth data for all the backscatter data sets. But in the Bay of Fundy, there are still some data sets that do not have ground truth coverage, such as areas like the small region in pink or areas up here, just smaller data sets that don't actually have ground truth samples. So to elaborate on the relativeness of each multi-beam survey, what this means is that sonars are generally not calibrated for backscatter collection. And due to this lack of standardized calibration, backscatter measurements are often quite relative to discrete surveys, and the consistency between multi-source backscatter data sets can be quite poor. And software like FMGT can correct for grazing angle and water attenuation, which impact backscatter intensity, but they cannot correct for the backscatter intensity differences between surveys. Hence why we get similar responses to the same bottom type, but the backscatter values are offset, creating a patchwork network like we see here. So if we were to sample the seabed in one area and we're able to relate the backscatter intensity to the sediment samples we have obtained, this information is relative to that data set alone, and it would be non-comparable with any other part of the data set. And while visually we can still interpret changes in bottom type here, like between surveys, we can still tell there's obvious differences between bottom types. Harmonization is required to get all the data sets on the same scale so that we can use it statistically or in GIS applications to identify continuous bottom types. And for habitat mapping, it means that without harmonization, our ground truth data can be used to calibrate backscatter and predict habitats within a given data set, but we wouldn't be able to use it over the full extent of multi-source data sets like Bay of Fundy. Because of this, absolute calibration is not possible, and therefore we rely on relative calibration, where each backscatter survey responds to bottom types in a similar way, but they are slightly offset with respect to the actual backscatter values recorded. And so to reiterate, previously there has been little research into methods for harmonizing backscatter from multiple sources. So originally the project considered classifying backscatter data sets independently, such as the work done by Lacherie, Brown, and Gazzola, and combining them afterwards. However, at least in the case of the Bay of Fundy, not all the data sets have ground truth samples, so we wouldn't be able to classify them accurately independently. And alternative research that was able to harmonize backscatter, such as the work done by the Ocean Mapping Group at the University of New Brunswick, use non-commercially available tools to generate a harmonized mosaic. And so while there is a harmonized mosaic available in the Bay of Fundy, the methods used to create the mosaic can't be replicated in other areas. And since this research was published commercial software packages have advanced, and we can now generate higher quality backscatter mosaics, applying all the necessary corrections. And so finally, a research paper published earlier this year by Niziak, Lashariti, and Brown was able to generate a harmonized mosaic over the full extent of St. Anne's Bank using the same bulk shift approaches we're applying in this project. The research proved the effectiveness of bulk shift methods. However, the St. Anne's Bank backscatter dataset was much newer and less complex compared to the Bay of Fundy. All right. Okay, so the new bulk shift backscattered normalization approach that was applied on St. Anne's Bank and in this project was developed by PhD graduate Ben Miziak to normalize the backscatter between different coverages using areas of mutual overlap for statistical calibration. And the results have been published in peer-reviewed literature, and the approach is now available as an open source method to run using R to harmonize any backscattered data set. The bulk shift method has been developed to calibrate or harmonize processed backscatter data sets quickly. In the northwest part of the Bay of Fundy, we'll look at for a demonstration. If we were to just mosaic the two layers as they are, we would get this patchy mosaic where there is an obvious mix match between the two data sets. The bulk shift method, on the other hand, is quite simple, where the model basically uses this area of overlap to calibrate them. And so we first extract the area at which the data sets overlap. And for each raster cell, we get two values for the two data sets. And you can see that although they have the same relative pattern, they are offset slightly. And so we basically treat one of the data sets as the reference or the target data set, and we use the other as the shift layer, and we calculate at every point the error between the target layer and the one we're correcting. We can plot this error on its own. If we sort the area, or if we sort the error by increasing backscatter, we can drive a model of the error between the backscatter data sets. This bulk shift model predicts how much every value in the shift data set needs to be corrected by to match the target. So what this is saying is that if you correct each of the values by the amount in the model, we should come close to the data set that we want to match. Then we take this model that we've derived using the area of overlap, and we apply it to the rest of the shift data set. It's worth mentioning that the R package and the bulk shift code uses multiple other models, not just a linear regression like the example I'm showing here. And you can also add multiple other covariates such as bathymetry to help predict the area. However, we found that using bathymetry as a covariate and the linear model is a good balance between flexibility and consistency of the results. But nonetheless, when you apply this procedure to the two backscatter data sets, it does a pretty good job of matching them up and removing that mismatch we see between two data sets. And so bulk shifting two data sets is relatively simple, but when we're dealing with a large and complex data set like the Bay of Fundy, certain considerations need to be made when you're choosing the order to apply the bulk shift. So first we wanted to start or choose a reference layer that shared an area of overlap with multiple data sets that had varying date of acquisition and frequency. We also wanted to start with a data set that was collected at a relatively moderate operating frequency, and these two considerations were made so that we could directly bulk shift many data sets to our reference, and also so that we could avoid shifting from very low frequencies to very high frequencies, which can cause problems. And lastly, we decided to harmonize all the data sets from one system and mosaic them into clusters, and then bulk shift those clusters together. Again, this was done to limit the issue of bulk shifting between frequencies and between data sets with large frequency differences. Okay, so when using these considerations, we can begin to harmonize one layer at a time, the Bay of Fundy data set, and mosaic the layers sequentially. So we chose 2 layers that were collected using the same sensor, and then we would bulk shift those together. Again, any other data sets that were collected using the same sensor were bulk shifted together into a cluster. And there are multiple other clusters within the data set that we bulk shifted together. And then we bring those clusters together and bulk shift them to each other in order to get this large coverage. And the same methodology is applied to other clusters within the data set. And then they're bulk shifted together. And then as we get into the older data sets, they don't share coverages that were collected with the same sensor or within any relatively similar period. And so they were just added to the mosaic sequentially later on until we reached our final harmonized mosaic. And so the bulk shift approach can be applied to multiple different data sets. However, the quality of the harmonized mosaic depends on the similarity of the data sets. Therefore, bulk shifting 2 data sets from the same vessel or the same sensor platform, although they are collected on different dates, tends to produce higher quality results. Another facet of the bulk shift procedure is the production of bulk shift statistics. So essentially, in addition to evaluating the quality of the results visually, we can assess the quality and accuracy of the bulk shift statistically. One option is through distribution plots, as seen here, which compares the distributions of data before and after the bulk shift. And essentially, we just want to see that the shift is going closer to our target data set. And another way to do this is through the error plots, or is through error plots. In a 2D error plot, we want the regression line to fit down the middle of the data points. In the case of poor quality results, you may see clusters plotting above and below the trend line. This could occur when another factor not being accounted for in the model is affecting the data, which is why we include things like bathymetry as added covariates in the model just to reduce that. We also found that the bulk shift approach was very effective at correcting for errors that are internal to a single data set. So in data sets like this one, the sensor used to collect the data was designed to change pulse length during the survey. And so there was an automatic change in frequency to account for changing depth. And artifacts like this feathering pattern are hard to remove through pre-processing. However, we found a relatively easy way to correct for these errors. And essentially by clipping each half of the feathering pattern and interpolating the target data set to reestablish an area of overlap, we can bulk shift the, good parts of the data together. And any remaining gaps in the data can also be interpolated to get a nice continuous harmonized mosaic. And once we generate our full harmonized mosaic, we can validate the quality of the mosaic using legacy sediment samples to see if it consistently represents substrate properties. And so we wanted to test if backscatter response can be explained by sediment properties. And because the relationship between backscatter and sediment can be non-linear, we fit a random forest model with backscatter as the response and sediment properties as the predictors. The out-of-bag estimates shown on the scatter plot suggest that sediment properties explained 51% of backscatter variance, and modeled predictions had a correlation of 0.71. Additionally, we assessed variable importance and found that the most important parameters for predicting backscatter were mean grain size and gravel percentage. This result is what we might expect from backscatter, which in part highlights the accuracy of our final harmonized mosaic. And finally, we generated partial dependence plots, which show the modeled relationships between the variables. And so the first plot here shows a large increase in backscatter with increased gravel percentage. And the second shows the same thing, an increase in backscatter with grain size. However, this one's on a 5 scale, so it's just inverted. Again, both these results we would expect from Backscatter or for, yeah. Sorry, now this is just an early exploratory analysis, but future work in this project will lead into further analyzing the accuracy of the harmonized mosaic and using it to classify bottom types. We hope to expand on the Become project and to explore the use of this data in species distribution modeling and bentoscape modeling using the ground truth data we have. And so that is all I have for you today. I'm open to any questions if anyone has any. Thanks for listening.
Hi, Clary. A nice talk. Questions? We have time for 1 or 2 questions. I think that Gary, nice talk, Clary. You have a question from Gary Green in the chat. It looks like you are comparing backscatter intensities, but I'm not sure how you deal with polarity. Can you start off by just reversing polarity to initiate your harmonization? Yes. It's from Gary.
Yeah.
Green.
I'm not sure if like reversing the polarity, we are just comparing intensities. I guess the whole point of this research was to see if there isn't a need for that. If you could just like, I guess, shift the intensity to be on the same scale as, or have all the data sets on the same scale to avoid that problem and see if it produced like a viable or an accurate result. I'm not sure if that answers your question.
Yes.
We didn't really consider polarity, I guess, is another.
Yeah, Gary's great take. He doesn't have one question, except you can fix the data I'm working on now in your spare time.
Send me an email. I'll help you fix your data set.
A comment from Gray. Okay. Yes, thanks, Clary. It's a very nice presentation. Okay, thank you.
Thanks for having me.
Okay. Now we have the next presentation. It's from Boni. It's from Federal University of Espírito Santo, sorry, Brazil. Okay.
Okay. Thank you, Teresa. Can you hear me well?
Yes.
Okay. Can you see my screen?
Not yet. Can you try again?
Now?
Yes.
Thank you.
In the presentation? Yes. Okay.
Well, good afternoon to all. My name is Carlos Boni, and it's a great pleasure to be here today and re-encounter the QHAB community. Today, I'm going to show you one of our previous seabed habitat mapping results entitled Reef and inter-reefal mapping using automated supervised classification. These results were produced by the Habitats Mapping Group, coordinated by the Professor Alex Cardoso Bastos. This data set is inserted in the context of the Aquatic Biodiversity Monitoring Program, created to evaluate the marine environment impact caused by the Fundão tailing dam failure that occurred in November 2015. The study area is located in the eastern Brazilian shelf in a coastal region of the Abrolhos Shelf. The survey covered an area of 26 square kilometers and was conducted using a multifrequency ultrasonic 2024 multi-beam echo sounder. Here I'm going to show you data relative to the 170 kilohertz frequency. Ground truth was obtained by footage from drop camera systems launched on 45 sites, selected after a previous analysis of the multi-beam data set. Some ROV and scuba diving information was used when available for complementary analysis. The study area was known as Forgotten Reefs, as it has been referenced by the local fishermen. Vieira and co-workers succeeded in mapping those reefs in 2011 with a side-scan sonar in a regional scale, classifying them as isolated biogenic reefs. Here we have some sonograms from their survey. Now we aim to map the distribution of the reef habitat and your relationship with the inter-reefal once its spatial coverage, origin, and habitat ecological significance of the structures is lacking information. We also use it high-resolution chart profiles from a previous multi-source seismic survey to increase our information about the reef's occurrence and define the multi-beam surveyed area. The workflow to produce the habitat map consisted on integrating in situ and remote sensing information. Two automatic supervised techniques were applied on the multi-beam data set, BRESS and RSOBIA. BRESS is a research tool developed by the Center of Coastal and Ocean Mapping from the University of New Hampshire, which performs an analysis of geomorphometric properties and landforms from bathymetry. Backscatter is then analyzed to derive seafloor segments based on similarity. RSOBIA is part of the maritime toolbar of ArcGIS and was created by OceanWise, licensed by partner Tim Lebas from the University of Southampton. And the scope of analysis includes image segmentation and classification based on slope, rugosity, and backscatter. Here we have the Batimetry Map. The seabed range from 10 to 24 meters. The reef structures vary in size up to 12 meters high and were found throughout three main regions. On the right, we have 3D representations of some structures. These regions indicate a southeast-northwest reef alignment with some coalesced structures, already described in the Abrolhos shelf. Bed forms known as furrows were observed with lengths exceeding 1 kilometer and width ranging from 3 to 24 meters. Here we have a bathymetric profile crossing these features. These bed forms were found not only on the inter-reefal areas, but between the reef structures too. The increase in the bathymetric information is quite significant when we compare the new 2 meters resolution data set with our previous regional bathymetry. Here we show the backscatter map alongside with the bathymetric one. The backscatter values range from -29 dB to -14 dB, and this heterogeneity can also be noted by the diverse scattering patterns of the study area. Due to logistic limitations and navigation safety reasons, the drop cameras were launched on the inter-reefal areas. Luckily, some of them capture reef structures, as the 21 and 29 drop sites. And the inter-reefal seabed varies from bed forms to the presence of macroalgae and bioclasts. Regarding the segmentation of the multi-beam dataset, BRES discriminated 8 classes, mainly summarized into 3: reefs, inter-reefal, and seabed associated with bed forms. Class 1 occurs primarily on the southern sector of the study area. The classes 7 and 8 are clearly related with the landforms geomorphometric classification, guided by crests and valleys of the furrows. 4 classes were distinguished by Arsobia, being 2 reef classes and 2 inter-reefal classes. A previous result did not differentiate the inter-reefal areas due to a configuration used to emphasize the distinction between the reefs. Besides, furrows were not successfully identified with Arsobia, it was possible to achieve a satisfactory inter-reefal classification, corresponding not only to backscatter and morphology variations, but also to macroalgae coverage. The southern reefs were also highlighted with greater values of slope and rugosity. With these semi-automated techniques, we managed to easily identify more than 900 reef structures and distinguish their morphology in 2 main types. The 2 distinct inter-reefal areas were mapped to reflect hydrodynamical regimes of the study area. Next steps of the research will be surveying and ground truthing the adjacent areas, focusing on habitat mapping, exploring the potential complementarity of these techniques, and trying to understand the uniqueness of the forgotten reefs, as well as the link between the furrows and geomorphological and hydrodynamical influence of the reefs. We would like to reinforce that these results are the only reef evidences mapped so far to the south of the coral complex encompassed by the Abrolhos National Marine Park. Thus, this habitat corresponds to an important reef hotspot on the Abrolhos Shelf, which is being mapped and widely known for the first time. Future studies will be also focused on the origin of these reefs, considering that the seismic data revealed paleovalleys in the area, and also the top of the reefs ranges considerably in depth. Well, that's it. Thank you all for your time, and there you have my email. Be safe, guys.
Okay, thanks, Gendre. We have time to questions. One moment. Questions?
Thank you, Camila.
One lapis. Ah, nice talk, nice image, nice data.
Thank you, Laps.
Yes. You are discovering the mysterious from the South Atlantic in Brazilian margin. Yes.
We are trying to.
A lot of reefs. Yes.
Yes, I think 962 structures, I think. That is the exact number.
Mm.
It's in a
900 reefs. Yes. 900 reefs, about 900.
Yes, in a small area, 26 kilometers.
Only in this small area.
Yeah.
Wow. Maybe we have like this in Pernambuco area, maybe. Yes.
Yeah, we hope so.
Okay. No more question to Gendre?
Thank you, Craig.
Okay. I can see the hand. I cannot see hand and the question. Okay, thanks, Gendre, for the
Thank
talk.
you. It's a pleasure to be here.
Okay. And then we move to the next presentation. We are go back to the Florida. The next presentation is from Michael Espriella, a PhD student from the University of Florida. Okay.
All right.
Okay. It's okay.
Hello, my name is Michael Espriella. I'm a PhD candidate from University of Florida, and today I will be talking about optimizing intertidal habitat classification at multiple scales using open source tools. So before getting into any of the workflow, I want to highlight the larger area of interest since I'll be referencing it often. So this red box is outlining Florida's Big Bend coastline, which is largely undeveloped and is home to estuarine systems such as Apalachicola Bay and the Swanee Sound. And we'll get a closer look at the study site, but it's represented by the black circle there within the Big Bend. The Big Bend has a variety of intertidal habitats, with some of the most notable being mudflats, salt marshes, and oyster reefs. And these systems are experiencing significant change as a result of stressors like coastal development, sea level rise, and in the case of oyster reefs, overharvest. In the Big Bend, there has been an estimated 66% net decline in area since 1982. And this decrease results in the loss of essential ecosystem services such as shoreline erosion control and water filtration. And while you'll see a lot of my talk focus on oyster reefs, really I'm trying to study these systems holistically. So as a result of these stressors, it's becoming even more important to monitor these resources in the Big Bend, particularly oyster reefs. There are two storylines that have compounded these stressors in recent years. So the US Supreme Court sided against Florida in a deemed water war, which potentially means less freshwater input, increasing predation and disease on oysters. Additionally, Florida closed the Apalachicola fishery for oysters, which is northwest of the Big Bend along Florida's panhandle. And while this hopefully will allow Apalachicola oyster reefs to recover, it can also result in additional fishing effort to the Big Bend. And even without this closure, the Big Bend had increased from 2% commercial landings in 2009 to 87% of the state's commercial landings by 2019. And while monitoring efforts have increased through interagency programs, there's still limited data, and sampling these intertidal systems is very challenging. You often need an airboat to access them, and your sampling time is dictated by the tides. So here's a closer look at the most comprehensive data that we have available. Just to note, these reefs are not to scale, but they were compiled, these data were compiled by the Florida Fish and Wildlife Conservation Commission. And as you can see, they're largely outdated and they've not been updated, meaning that many of these reefs are no longer there. And here is the specific study site that we'll see in a second, Little Trout Creek. Given all this, the objective here is to develop a semi-automated and repeatable workflow to monitor changes in intertidal habitats in a cost-effective way. More specifically, the goal is to generate workflows that can be run on imagery and consistently produce high-quality habitat maps so we can start to observe temporal changes and understand spatial relationships. We chose to use drones to accomplish this objective as the platform, as they're inexpensive and have a lot of flexibility regarding when you can collect data, which is important given the difficult working environment. And there are some studies that have used drones to monitor oysters, but those are largely conducted using manual delineation, and we really want to cut down on that time-intensive processing. So first, overlapping drone imagery was collected at Little Trout Creek using an unoccupied aircraft system or drone equipped with a red, green, blue camera, so just a normal camera. Then using Pix4D Mapper, an orthomosaic and digital surface model were generated from the imagery. And these yellow triangles on the orthomosaic to your left represent the ground control points that were used for georeferencing. And you have the digital surface model on the right with the red areas representing regions of higher elevation and the blue areas of lower elevation. And since this is, all this imagery is coming from a drone, everything that you're seeing is either at or above water level. However, you will notice significant artifacts here as a result of difficulty with finding matching key points when stitching the imagery together, because the water is of course in motion while the camera is taking still images. So here I just want to illustrate quickly why, in part, why this is a difficult environment to work with and the scope of habitat mapping. So each habitat here is represented by 4 pixels from the scene. And if you looked at this, you would probably have confidence that the computer could classify these cover types. However, in reality, a lot of the scene is covered in mud. And this is what the pixels will typically look like. These are also 4 pixels drawn from each cover type. As you can imagine, this makes it very difficult for classification algorithms, especially while using pixel-based analysis. So you relied on object-based analysis, which first segments pixels based on criteria for homogeneity, and then classifies those objects using additional information such as geometric indices and perimeter and values like that. So given this spectral similarity, again, object-based image analysis was employed for the classification. And this initial processing was conducted in eCognition, which is a proprietary software. But as you'll see, it was expanded to be open source. And I just want to present these results to show you kind of the differences between the results that I got. So the water was removed in an initial segmentation and classification using a water index and the elevation data from the digital surface model to minimize confusion with the intertidal habitats. Following the removal of the water, it was segmented once again, and those objects, 20 objects from each habitat class was selected to train a standard nearest neighbor classifier. 31 variables available within the eCognition software were tested to determine which 10 allowed for the highest level of separability between classes. And then a nearest neighbor classifier algorithm classified the remaining objects. And one thing to note here is that this entire workflow is then built into a shareable rule set that can then be run without really any manipulation on a similar scene, significantly cutting down on processing and analysis time. So this is the resulting habitat map. You can see the relative areas of coverage there. And then I used over 600 points in a stratified random sampling scheme to assess the accuracy of the map, which resulted in an overall accuracy of 79% and a kappa of 0.72. So looking further into the accuracy, here's a confusion matrix breaking down where misclassifications occurred. And for the purposes of the study, I really want to highlight users accuracy, which is an error of commission, so how often an object is erroneously included in a class. And the reason I want to highlight this is because this is intended to be useful for managers, the user's accuracy is really measuring reliability, and it's a useful metric to kind of demonstrate how useful this product might be. The distinction that had the most trouble, as you can see, was Martian oysters. And this can be for a number of reasons, but one explanation was, if you recall, and we'll see the scene again, but a lot of the marsh was on the edges of the scene. So within this e-cognition workflow, geometric indices were a little bit skewed because of artificially smooth edges for the marsh class. So we were able to successfully, develop a repeatable workflow that classified intertidal habitat with high accuracy. However, eCognition is a proprietary software, so I wanted to know how can we make this more accessible. So I came down to 3 main sub-objectives, which were use an open source workflow, limit the input data. As I mentioned, I tested 31 variables, which was computationally intensive. And test multiple resolutions. The initial workflow only tested the native resolution of 6 millimeters, which again is computationally expensive and potentially can introduce noise by just being unnecessarily fine detail. So as I mentioned, I resampled the resolutions and I went from 5 to 31 centimeters by increments of 2 centimeters to observe any trends or drop-offs in classification accuracy. Here we can visualize the decrease in detail as the resolution coarsens. So 31 centimeters was selected as an upper bound to correspond with what is achievable from other remote sensing platforms such as manned aircraft or satellite. You can see a ground target here, so you can really see how that changes over the resolutions. And I know I include 1 centimeter here, but I'm not indicating that it was tested, and I'll have more on that later. But for now, just to highlight the differences here, the 1 centimeter orthomosaic was 13 gigabytes in size, while the 31 centimeter orthomosaic was 15 megabytes. And that really cuts down on processing time. So to make the workflow open source, it was conducted in R using the SegOptim package. If you recall yesterday, we had a presenter, Aaron Sleep, who used it as well, which is great to see because I think it's a really underutilized tool. But this package, as a reminder, allows you to access a multitude of segmentation algorithms. And most importantly, it minimizes parameterization bias by testing a range of parameters on a subset of the scene. So given I was testing so many resolutions, I wanted to be sure to minimize any parameterization bias as much as possible to ensure that differences in the results were not caused by me arbitrarily selecting parameters each time. So I gave the optimization function this training set here and a range of parameters to test for the segmentation. And the result was the combination that produced the highest kappa in a random forest classification. And then those were then applied to the entire scene. Only the means and standard deviations of the orthomosaic and digital surface model were used to inform the classifier. If you recall, 31 variables were used in the eCognition workflow. So this really simplifies processing and hopefully encourages managers to use this method given the more attainable inputs. Again, a stratified random sampling scheme was used to assess the accuracy of the habitat maps. And you can see the resultant overall accuracies to the right here and a 5 centimeter habitat map to the left. Although we do see a drop off there for 19 centimeters, all the resolutions performed well as far as overall accuracy. A reminder that the proprietary software produced a 79% overall accuracy, and many of the resolutions here performed as good or better than that. Once again, looking at user's accuracy because of its relevancy to the objective, it's broken down by the highest per cover type, and water and mud perform better at finer resolutions, while marsh and oyster performed better at coarser resolutions. This was the opposite of what we predicted, given the more fine scale features associated with marsh and oysters. But the larger point here is that different habitat features are highlighted at different scales. So perhaps one scale is insufficient to study these systems. This is just displaying the two methods side by side. To the left is the classification conducted with eCognition, and to the right is an example using the 5 centimeter classification with the open source workflow. So in conclusion, open source tools can be used to develop high quality habitat maps in Big Bend's Intertidal. We saw that accuracies were on par with the proprietary software, which will hopefully encourage state agencies to pursue this method and monitor these resources more closely. Coarser resolutions performed just as well or better than finer resolutions, meaning that for habitat classification purposes, it may be unnecessary to target such fine resolutions when you're in the field. And this finding can reduce both field time and data processing time. I mentioned the 1 centimeter resolution earlier, so I just want to note here that I intend to test both 1 and 3 centimeter resolutions, but I don't have those results yet today, partly because that optimization process is so computationally intensive for large data sets. So those are currently processing. Perhaps the most important point here is that this allows for consistent monitoring, which is currently lacking in the region. Developing tool sets to quantify change and identify spatial relationships between these habitats is essential to managing the resources. And this workflow is repeatable with minimal adjustments needed for a new data set, which is something that will be tested in the near future. And they can be expanded to areas as well with different cover types. Additionally, future work will look at what different sensors can tell us about the intertidal habitats. So LiDAR has now been collected over this scene that you've been looking at, and comparisons will be made to identify any trade-offs between LiDAR and just traditional RGB imagery. With that, thank you for your time, and I'll open it up for any questions.
Right. Thanks, Michael. Questions? Alex Ilich, please.
Yeah, thanks. I really enjoyed that. I've been interested in object-based stuff, and especially I'm a big proponent of open source software, but hadn't really found a good way to do it. You mentioned, though, that different scales were important for different types of your habitats. Is it possible to have a multi-resolution model? Because I know with eCognition, the thing that they always advertise is that it's like a multi-resolution segmentation or something like that. So is there a way to do that with the open source tools?
Yeah, so the short answer is no. The longer answer is it's definitely something that I'm looking into, and kind of where I want to take it next because of those differences. We have kind of done a workflow more with texture, like roughness, that has incorporated them. And then, so that's one step, one of our next steps to incorporate that. In eCognition, step 1, to see for like a feature space analysis, if that's held, high up there, if it's an important variable. But yeah, I've been, kind of brainstorming ways to include them all within the same workflow, but it's not readily available, so it would require some manipulation.
Okay, thank you.
Yep.
Okay, more questions? Yes. No more question. Thanks, Michael, for the presentation. Oh, one here.
Sure.
From
Yeah, I have
Mark.
one here. How did I select the segmentation algorithm, and if I explored any other segmentation algorithms? So I actually started with a k-means segmentation, and it had a lot of difficulty with artifacts along the flight lines. So that's why I shifted to large-scale mean shift. It was able to kind of ignore those flight lines more so. So if you can imagine, the objects were all constrained by each line. So that's why I ended up picking that one. It was much better at dealing with those artifacts. Also, it seemed to process the large data sets a little bit better, and with that tool set, you can do tile-based analysis as well.
Okay, we have time to questions. I think that we have no more questions. Okay, thanks, Michael.
Thank you
for the presentation. Okay, and now the next presentation is from Marcos Leite from Federal University of Espírito Santo. We are go back to Brazil orders.
Hey, Teresa, can you hear me well?
Yes.
Okay, let me share my screen. How about my screen? Is that okay?
Yes, it's okay. Okay.
Okay. Let's go. So, hello, everyone. My name is Marcos Daniel, but please call me Daniel. Currently, I'm a JADCO scholar at the Center for Coastal and Ocean Mapping at the New Hampshire University. The subject of my talk is based on the parallel research I've been developing with the lab I used to work in Brazil, the Marine Geoscience Lab, with Professor Alex Bastos. And also, we have been working with Joana Gafeira from the British Geological Survey. That's the title, Applying Semi-Automated Maps for Identifying Seabed Cyclone Depressions at the Brazilian Outer Shelf. So my talk will be in 4 parts. The first part, I will give you an idea of how we got up here, mapping circular depressions. Then the second part will be the methods. In the third part, I will focus on our results so far. And finally, I'll go and talk about the next steps. Now, let's turn to the first part of my talk. A few years ago, the Marine Geoscience Lab acquired multi-beam ecosystem data in 3 areas located on the outer shelf of Western Brazil. The research focused on incised values. From that data, masters and PhD have been reading their thesis, and the data set gives us a good insight with the complexity of the area. Here on the left, in that map, we can see how the resolution is much, much better with the multi-beam echo sounder. In 2019, the lab started to survey areas beyond the pilot channels. The research focused on recognizing and identify vulnerable spots on the continental shelf due to the Mariana Dam's failure disaster. Based on the previous data resolution, it seems that the survey would be boring, pretty boring to be honest. And it turns out we stumbled across thousands and thousands of circular depressions. So let's map those features. But manually mapping each circular depression would have the mid unsuitable. First, it can be extremely time consuming. And second, it's implicitly subjective. And to avoid it, based on papers of Gafeira and Pica, the circular depression were classified by Batimetry position index, computed using the BTM toolbox, and the sequential use of several standard ArcGIS tools to delineate and characterizing the circular depression's features by extracting water depths, backscatter intensity values, and morphometric information for each depression. That concludes how we got up here. Let's move to the mappings. So that's the story area. It's located on the Western Brazil outer shelf. Depth range from 43 to 320 meters. The black dashed lines represent the resin data, and the blue dashed lines the 2024 data. The multi-beam data sets comprising areas of 230 square kilometers and 2 meters horizontal resolution. Bastos classified the shelf as a paleovalue shelf. As the name suggests, this region is morphologically characterized by incised shelf valleys with heterogeneous seabed composed of rhodolites and mixed carbonate sediments. The resin data was characterized by artifacts due to tidal shifts in the lines overlap and the system misalignment. The literature recommends applying a smooth tool in those type of data, and then using any math to classify the feature. Unfortunately, the final Batimetric smooth data hide most of the features. So the final approach was a manual mapping, only to complete the density distribution across the area. For the 2024 data, we used a fine BPI to identify circular depressions. The BPI put radius values used to classify and extract the filters were adjusted manually to determine the most realistic outputs. And the resulting classified BPI rasters were exported to polygons. And from this point, I based my analysis on Gafeira's papers. By well-defined tools on ArcMap, such as buffer, smooth, extract by mask, and so on, I was able to delineate each feature and to obtain the depths and backscatter intensity values for each circular depression. And the threshold value applied was 50 square meter. And after that, visual assessment was carried to delete incorrect polygons left. And the video analysis were carried by visual analysis. Finally, I compute the minimal water depth, the maximum water depth, the vertical relief, which means that that's the height of the future, the vertical relief area ratio, which will describe how complex is that feature, and the profile indicator. And the profile indicator will tell me if my feature is a V shape or a U shape. And in order to generate a density map, a centroid for each depression was computed. So now we came to the next point, our results so far. This map shows all identified circular depression as black dots, both manually and semi-automated. 3,660 circular depressions were mapped at water depths range from 46 to 85 meters. The same automated approach has identified 2,648 circular depressions, and the manual map has identified 1,012. So the numbers 1 up to 4, it's just zooming areas over the study sites. And here it's the red line just represent the final delineation of those features. Here on the left, it's a habitat class map. Natasha has showed that map yesterday during her talking, On the right side, it's the density map. So the highest circular depressions density occurs from the center of the stir site toward the south, mainly between the incised valleys with a density of almost 6 circular depression per square kilometer. The higher density is mainly associated with Moore classes and the Paleo-Valio classes. So from the center toward the north, the density decrease. The habitat class shows higher concentrations of rhodolites. And besides, there is a hard ground bottom at depth of 60 meters. Those might control the number and also the area and the vertical relief of those features in that area. The circular depression areas varies from 50 square meters to almost 460 square meters. The median area of the circular depression, it's 160 square meter. The stacked histogram shows that most of my data located on the depth range from 50 up to 6 meters. The largest mapped circular depression, I mean the vertical relief, the height of it's 5.2 meters depth, and the shallowest one is 0.3 meters. So I just would like to highlight here that 75% of the data are shallower than 1.5 meters, and the mean vertical relief value is 0.9. So we're talking about small features. And at the same way as before, the stacked histogram just showed most of the data, looking in a range from 50 up to 6 meters. So in that slide, I would like to show you the shape of the circular depressions. A higher vertical relief area ratio corresponds to single circular feature, and a lower profile indicator value corresponds to a V profile feature, a V profile. In that case, most of the circular depression presents a less complex shape and has just a V profile. I would like now to change direction and talk about the backscatter. The first analysis has shown a trend on lower backscatter intensity values inside the features than in adjacent regions. Here, in those graphs, you can see 6 profiles across the story area. The Batimetry profiles shows the circular depression features. And I would like to highlight the vertical relief, which ranges from 0.5 meters up to 3 meters. And here at the bottom, it's the backscatter intensity values profile. Both profile, same distance, same points. And as you can see, most profiles will show that scenario, a lower backscatter intensity values inside the filters rather than in the adjacent regions. So far, we got 2 videos from the circular depression. It turns out it was possible to observe accumulated macroalgae inside the depressions, which could be affecting the response of the backscatter. Exciting, isn't it? In the left picture, you can see a screenshot from a drop camera at the water depth of 50 meters. And on the right side, it's just a screenshot of ROV just flying one of the shell files at 7 meters. Let me just play a short video for you guys. So look at this video. Mighty. There is a hydrodynamic control because one side of the circular depression is plenty of algae and the other side it's not. And I do believe the investigation of those features will bring a new discussion on the role of these microhabitats at the regional scales. I've been wondering regarding the origin of those features, and I'm sorry, fellows, there is no answer yet. Perhaps next year, on the next you have, but we do have some hypotheses. One, all those areas around the incised valleys could be rich in organic matter. Therefore, a flowing fluid process could destabilize the transverse deposit, forming a small pockmark. And two, it's a biological process, perturbation, fish. Let's see, we'll find out. I would like to end with the next step. First of all, it's just the confidence assessment. I'm going to compare our results with the seabed map toolbox. Also, I would like to focus on the backscatter analysis. I would like to check if there is really that difference inside and adjacent regions, and if it's possible also to analyze if there is a distinct algae segmentation distribution. I also would like to check and see what is the distribution related to each regional habitat class, and why not new data? Sediment samples with scuba diving could be amazing. More videos, scuba diving, ROV, and water column data could be a really nice one, a really nice choice. And also a high resolution seismic data. Well, I've covered the points that I need to present today, and I'd like to thank you for taking time out to listen to my presentation. So now it'll be very interesting to hear comments, questions. That's my reference. Thank you.
Hi, thank you for the presentation. It's more mysterious from the Brazilian shelf, continental shelf. Questions to Daniel? Gary, please.
Yeah, that's a very interesting presentation. You've certainly done a lot of work on those, what looks to me like pockmarks. But the interesting thing would be to find out how old they are. They could be quite old, actually, if there's been no disturbances like fishing efforts and what have you around there. The other thing is that, did you see anything in those pockmarks like a little point inside? Often with methane, if methane is coming out, it'll change the chemistry, and you can have calcium carbonate in the center of these pockmarks, and they can tell you something about the fluids that are coming out if they are fluid derived. So I would think one of the things you might want to do is to take a look at the center of these things. You said you found algae in there. The work that we've done along the California coast, we found plastics in these things. A lot of plastics seem to accumulate on there. And then this plastics actually forms a substrate for anemones. So we would go around and see all these pockmarks, they have anemones in them. We think, oh my gosh, there's calcium carbonate there. There must be methane. I did this with Charlie Paul at Imbari, and we found out that no, they're just trapped plastic and became an artificial substrate for sea anemones. Anyway, a very interesting talk, but I think you need to pursue that. Pockmarks seem to be the thing. It could be biogenic. There's been tile fish that produce such things on the Florida coast. But a nice talk. I'd like to see you further sample the area.
Okay, thank you.
There is a question from, a moment. Aaron, yes, can you?
What
can
you
you
hope to answer with the stable isotope analysis, the origin. We can talk about the origin of those guys, and that's the idea.
Okay. More questions? Yes. Karen? Thanks for the clarification. More question? Yes, I hope so, to clarify these mysterious holes. Do you think about pockmarks or not pockmarks?
To be honest, I'm not sure. I first thought, yes, it's a pockmark. We think about all the history of sea level change and what do you have on the actual coastline. So yeah, probably, but we need to go further. We need to sample some sediment data. Just with that, I can tell you, yeah, that's a pockmark. No, that's not a pockmark.
Okay. We have a question. Can you read? From Ben and Greg.
There is one from, let me see, great talk, Dan. I hope it clarifies. Okay.
From Ben.
Great talk, very soon. What type of info push scores are you hoping to be able to get with divers? Those type of small cores could be inside and just around the future. So from Craig, great presentation, Daniel. Interesting correlation between your bath and Backscatter. Is the algae washed in from elsewhere? And do you know if it's changed seasonally? Yeah, it's changed seasonally. As far as I can remember, I had that talk with Gabriela Leite. She did her Master of Science, and she did tell me this, that there is a seasonal change.
Okay. More question? Okay, no more question. Good luck for the clarification, Daniel. Maybe in the next you'll have. Okay.
I hope so. Okay, yes. Thank you, guys.
Okay, thank you. And then we go to the next presentation from this section. It's from Camila Silveira, a postdoc from my university, from Federal University of Pernambuco. Camila, please.
Okay, hi everyone. Is my audio okay?
Yes, it's okay.
Okay, great. So I'll start sharing the screen. So can you see the full screen?
Yes. Okay, it's okay.
So hi everyone, my name is Camila, and I'll be presenting today a chapter of my doctorate thesis entitled Coral Reef Mapping Using Satellite Imagery, a contribution for seascape management. And as I said, this was developed during my doctorate and when my supervisor was Professor Beatriz Ferreira. So this is basically an overview of what we are going to see in the next slides. So what we wanted to do was mix in situ data and environmental layers and put that into a species distribution model. And with these results, we wanted to correlate that with use layers. Basically, the two questions, the two main questions in this research were, where are the large colonies of Millepora auscornis, which is a coral species, and why are they or aren't they there? Here is our study area. So it's a region in south of Pernambuco, northeast of Brazil. It's a coral reef area. So we were shallow, so we were able to map it with satellite imagery. So it's a different approach from what we've been seeing here. And this area has overlapping MPAs. And the study area is a mosaic of interconnected habitats. We have mangroves, seagrass beds, estuaries, coral reefs, and to the deeper part of the continental shelf, we also have mesophotic reefs and shelf valleys. Our study area is also within an international long-term ecological research site, number 18. In Portuguese, it's called Pé de Tams. So all of these habitats, they call for an urgent need of detailed and so in this research, we're going to focus a little bit on the coral reefs of these regions. They have this singular pattern of 3 lines of reefs that are almost parallel to the coast, and this also can influence in this species distribution. If you're interested, we also have mapped the shelf valleys of the area, and here is the paper. So back to the coral reefs, they are considered biodiversity hotspots and priority areas for management and conservation. They are important biologically, ecologically, as protection to the coast, and also they provide goods and services such as tourism and fishing. So the main objectives of our research were to map areas of high biodiversity, to identify where the largest colonies of Millepora auscornis are, and to answer these 2 questions. Is coral distribution only controlled by environmental variables in our study area? And 2, once environmental thresholds are reached, are human use and conservation measures the main drivers of ecosystem development and maintenance? So for that, we had to integrate cost-effective and multi-resolution remote sensing techniques, species distribution models, and human use layers on shallow water coastal reefs. With that, we hope to aid and help the management of the marine protected areas and other protected areas in the region. So why did we choose Millepora auscornis? This coral species is called the fire coral because it's very stinky, and it's probably, as we're going to see in during these presentations, probably the main reef builder of the area. Also in a lot of other tropical reefs. They are very three-dimensional and they harbor a lot of different fish and invertebrates within their colonies and adjacent area. On the other hand, as well as with other corals, they are subjected to a variety of impacts, global impacts and local impacts. Here on the right, we can see the corals in the area and one of the most intense bleaching that happened so far, which was in the last year. So an overview of our methodology, we had to gather species presence data, as well as build our environmental layers. So these layers were ecological, topographic, and local. And with that, we could build our model of species of habitat suitability. Also, with that results, we wanted to compare that with the use layers like tourism and fishing in the area. For the species presence data, we did a lot of field work. And let me just turn off the sound here. So here's like a video of our field work. So we had video tracking in photo quadrats, and then we geotagged them and put them into a georeference database. These were done by diving most of the time. And we also did underwater sensors following a reef check methodology in some of the sites with fish, substrate, corals, invertebrates, and algae surveyed. This is part of our continued monitoring by reef check and pellet dumps. So here is how our GIS database looked like. So we have information on corals, on benthic classes for each of the photos and frames that we had. So for example, this is a photo of a frame of a video showing 7 colonies of Millepora ossicornis. Our final Millepora map. Here we can see the black dots is the black point, sorry, is where Millepora was absent. The white ones where he was present, and the red ones where we found colonies that were larger than 100 centimeters. So we wanted to put in the model only large colonies because we know that this coral can reproduce by fragmentation. So it can sometimes colonize areas that are not optimal for its growth. So they are probably only small colonies in these places. So in numbers, we had more than 7,000 total frames. In this, out of these, 859 total presence of Millepora and 222 points where we find colonies larger than 100 centimeters. So going on to the environmental variables, the ecological variables were calculated and derived using Worldview 3 scene, which has 2 meters per pixel. So we did habitat mapping, habitat diversity per area, and major cover per area. Here are the results of our benthic mapping. So I can't take too long in it, but if we have time in the end of the presentation, I can show you all of the classes, a picture of all of the classes. So we did a selection of the benthic covers that best represented each area. We did all of the steps, post-processing steps, segmentation and classification, and we used a machine learning supervised method called support vector machine classifier to classify this image with an overall accuracy of 79%. We ended up with 15 classes. As you can see, some of them are hard substrates and some of them are organism related, like Palitoa caribeorum and the Millepora ossicornis, which itself had a different spectral signature than other classes. So we were able to map the colonies and the areas that had large colonies, larger than the pixel, of course. So here's a zoom in of some of the areas, the top area, central and bottom area of our study region. And with that benthic cover map, we derived habitat diversity and major cover. We were able to see areas of high biodiversity, usually associated with the reef edge, to recognize and to visualize some of the fragmented reef areas, which we called coral reef rubble. And we saw that the reefs, they have defined zonation, usually with a flat made of palitoa and rock, and the inner edges of the reefs with algae. So now we have to derive our topographic values. We did that using multi-resolution satellite imagery, Worldview 3 and Landsat 8. Actually, as these had a lot of different steps, we published an article with the methodology steps and everything and our results, and we used that to calculate the other derivative layers like BPI, slope, rugosity, and aspect. here is the derivative layers. And now to the local layers, we found it was very important to put that into our model, like distance to shore and turbidity. So distance to shore was calculated using a simple algorithm like the difference from each pixel to the line of the coastal line. And turbidity, we wanted to see how it varies in our study region, and we calculated that also using satellite imagery, Landsat 8, in Accolade software. So now we have everything we need to derive our MaxEnt model and our map of suitable habitats for the presence and growth of Millepora ausculens. So our model showed that our top 5 most influential values were ecological layers like habitat diversity in all 3 grid sizes. We can see that this is closely related to a healthy reef ecosystem, a lot of habitats in a small area. Also with habitat cover, as expected, we can find that Millepora habitat signature was a suitable habitat for Millepora ausculens. So, but they are also highly correlated with reef rubble, which are the fragmented reefs, and the calcareous mat, which is the main benthic cover found on top of the reefs. And our model had an AUC of higher than 0.97, which renders this an excellent result. The topographical and local layers were also important, and Millepora showed close relation with bathymetry. Usually prefer shallow areas, optimally from 1 to 5 meters deep. The distance to shore, I showed you, I don't know if you remember, but that 3-line patterns that the reefs are organized. We see here the first line, and the second peak is associated with the second line of the reefs, and the third line doesn't appear here, doesn't show in this graph, probably because it's a deeper area and also with high turbulence, has a lot of wave action. So not an optimal place for branching corals to develop. Also, the BPI was positive, and these values are usually associated with the reef presence. Here is our final habitat suitability map for the Millepora, and I've circled some of the regions where we expected to find large colonies, but we went there afterwards and we didn't find it, or we only found small colonies. So why? Basically, when we put our human use maps in our research, we saw that fishing and tourism are impacting the growth and the settlement of these colonies. So our question of our environmental variables, the only factor limiting and controlling the settlement and growth of Millepora ausculens colonies, probably not. Probably the human use is also impacting these areas. So we derived this fishing map and tourism map. These activities in the area, they are highly associated with coral reef areas. So the last thing is that I would like to ask you this. So what's more important is nurture. So how we take care of the ecosystem or nature. So the basic topographical values that we find in this area. So with that, I finish my presentation. I would like to thank GeoHub for having my presentation here, and I apologize for any mistakes. I'm not a native speaker, and thank you in general. Here's my contact and my lab website.
Okay, thanks, Camila, for the presentation.
Sorry.
Questions?
Sorry.
One moment. Question to Camila?
Thank you, Vanessa. I'll stop sharing the screen.
Yes.
Okay.
No question to Camila? Congratulations. Gary? Sorry.
Hi, Gary.
Hi, that was a very good talk. I would be interested in the anthropogenic impacts and what you may be doing with those anthropogenic impacts. I imagine fishing is one of them. There are probably some other things. Scuba diving could be also an impact as well. I'm also thinking, would you be willing to submit a paper to our special issue on the impacts that are occurring on these coral reefs? I think that would be a very significant contribution.
Thank you for the invitation. Yes, I would be happy to do it. We are currently investigating the anthropogenic impacts, but the thing is, in 2020, we weren't able to access for the majority of the year. We couldn't do any field survey because of COVID restrictions in the area. So basically, we stopped going to the field in March. So it was when the bleaching was occurring. And we also have some other anthropogenic impacts in this area, like the vessels that they use. Sometimes they break the reefs and the corals. And so, yeah, we've been studying these reefs for some time. And I think that only if we could map the anthropogenic impacts, it would be great.
Okay. More questions to Camila?
I think no.
I think no question more. Thanks, Camila, for the presentation.
Thank you, everyone, for the congratulations.
Okay, thanks. And now we are finished with this section. We thank all the presenters from this section. And now I think it's break time, okay? Thank you.